Chapter 16, number 29. For each dozen eggs, you expect a broken egg. You expect 0.6 broken eggs. And the standard deviation of that is 0.5. This is given information. We're going to treat these as random variables. So for 3 dozen eggs, mu is going to equal the sum of the means. So it's going to be 0.6 plus 0.6 plus 0.6, or 1.8 eggs broken per 3 cartons of eggs. The standard deviation equals the sum of the variances. The variance equals the standard deviation squared. Standard deviation equals the square root of the variance. So the standard deviation for the broken eggs is going to equal the square root of 0.5 squared plus 0.5 squared plus 0.5 squared. This is the square root of 0.75, which is about 0.866. To add the means of the broken eggs for each egg carton to get the mean of all 3, the cartons must be independent. Similarly, the cartons must be independent in order to find the standard deviation of all 3 by taking the square root of the sum of the variances. Number 33. Okay, there's trucks. Each truck averages 1.3 tickets a month with a standard deviation of 0.7 tickets. What is the mean and standard deviation for 18 trucks? Well, the expected number of tickets is simply going to be 18 times 1.3, or 23.4 tickets a month. The standard deviation is going to equal the square root of 18 times 0.7 squared. In other words, it's the square root of the sum of the variances, which is 2.97 tickets per month. In order to do this, we must assume that the trucks are ticketed independently. Finally, number 35. Okay, an insurance company selling fire insurance for homeowners. The expected annual cost, the revenue that they're going to get from each policy, is $150 with a standard deviation of $6,000. Now, why is there such a big standard deviation, or the variance for that matter, which is over $1 million? Let's see, 6,000 squared. That would be, is that 36 million? I think so. Let's see. 6,000 squared. 30, let's see, 1, 2, 3, 4, 36 million. Okay. The variance is 36 million. That's really a lot. Okay. Why is the variance so big? The variance and its square root, which is the standard deviation, is used to measure, in something like this, it measures risk. That is, it measures how big the profits can vary. Now, in this case, the company would not expect a gigantic profit of $36 million. Instead, what would happen would be a big loss of $36 million. And now that could happen, not on one house. Well, it depends on how much the house is insured for. But the house can be insured for quite a bit. Anyway, so that's, in general, insurance company, there are many small profits, right? These in payments, $150, $150, and then once in a while a home burns down, and then they got big losses, okay? The cost of the house, the property, there could be injury, all sorts of different things. So I have the expected value here. The standard deviation. So the standard deviation of the profits is highly variable. Now the situation is reversed for policyholders. In other words, they make many small payments, and then every once in a while, it's a little bit like the lottery, buy lottery tickets. Insurance is a lot like the lottery. You make these little payments, and then every once in a while there's a very dramatic profit. Your house burns down, and you get all this money back from your little payments. Okay, now what is the expected profit and standard deviation for 2 policies? 150 plus 150 is 300. For the what's the standard deviation for two policies? It's the square root of the sum of the variances. So 6,000 squared plus the square root of 6,000 squared plus 6,000 squared, which is $8,485.28, approximately. Now, what is it for 10,000 policies? Well, the expected profit is 150 times 10,000, which is, let's make sure I got this right here. 15 followed by 1, 2, 3, 4, 5 zeros. 15 followed by 1, 2, 3. Okay, so that's $1,500,000. Now the standard deviation is the square root of 10,000 times 6,000 squared, or 600,000. Okay, now let's go to D. I did E and then I should have done D. Okay, if profit is reward, are they likely to make money? And standard deviation measures risk. The risk-reward ratio decreases as policies increase. For one policy, the risk-reward ratio is 6,000 divided by 150, or 20 to 1. In other words, the risk is 20 and the reward is 1. For 10,000 policies, the risk-reward ratio is 600,000 over 1,500,000, which is 3 to 5. And obviously, that's a much better ratio. Now the denominator is bigger than the numerator. In other words, the reward is starting to exceed the risk. So profit is likely at 10,000 policies sold. Now, what do these calculations depend on? They depend on the homes being independent of each other. If a wildfire threatened an entire area of homes, all insured by the same company, then the homes would not be independent, and the company, all of a sudden, then the risk ratio would not hold, and the risk ratio would the risk, the numerator would get really big. The company could be wiped out.